First of all, I really want to appreciate the workshop or the trainings that you have arranged. So it's a great opportunity to present the work I have worked on, or even other scholars and researchers have worked. So I'm really thankful for that. So, as already you have mentioned that I have worked on the integrated multi-hazard assessment using machine learning in the complex terrains of northern Pakistan. As we all know, the natural hazards are globally causing many destructions, causing infrastructure damage, economic loss, and also causing affecting the ecosystems not only within a specific country but to all the world. I mean, globally they are causing the devastation and destructions. And important thing is that climate is actually changing. Many researchers and studies are working on the climate change, but specifically, if we see to the northern Pakistan, we have a complex terrains. I mean, you have multiple hazards that that is exacerbated by the climate change, rising global temperatures, and specifically the glaciers are actually retreating. I mean, they're melting rapidly. They are actually causing the glacier induced flash floods, and the rivers are actually rising due to their sudden breaching. I mean, so they can cause the flash floods within I mean within few minutes, hours. So no one know due to the lack of early warning system, specifically in a country like Pakistan. So we need these kind of studies further to integrate multiple hazards and work in the complex terrains of northern Pakistan. So in this study, we will know how the machine learning can contribute to the multiple hazards, not only with specific hazard, but multiple hazards. We have considered in this study multiple hazards. The reason behind is that specifically the Delhi et al. 2005 study, they actually reported that globally around 30 million kilometers square of land and over 4.3 billion populations are exposed to at least one natural hazard, and 3.5 million kilometer square area and 700 million people are exposed to two and more hazards. Similarly, there are other numbers like 105 million people are exposed to three or more hazards. So if we see all these exposures, these are making, or I mean, where the peoples are exposed, the constructions are exposed to these hazards, but still people are actually relying on these single hazard studies, and they are actually not considering the multiple hazards, as these hazards actually occur as the as a cascading events. Even sometimes one hazard can cause another hazard, and we have actually ignored the multiple hazards in such mountainous areas. So the population's growth is also rising, I mean increasing in these northern Pakistan and in these elevation areas, and vulnerability of infrastructure and economic activities are also rising, and the communities who already marginalized their stay living there, they are actually on a high risk to multiple hazards. So the multiple hazards, somehow a new study, people are focusing on this since 2000 or 1996, that is still under development, but these studies are gaining a momentum in hazard prone countries to developing disaster risk reduction policies and measures. So the methods specifically are varying for, if someone is working on the multiple hazards, there must be different methods for the multi-hazard assessment. People are using a number of methods to assess the multiple hazard, like some people are rely on the objective methods, some are actually relying on the subjective methods. So statistical approaches like adaptive regression, splines methods, and logistic regression and generalized additive models, and specifically analytical hierarchy process (AHP), which also use the scales for its importance, for factors importance, like say SETI 1980 scale they use. So many studies has highlighted these methods to assess the multiple hazard through these methods. However, in machine learning, actually, people are getting more interest in machine learning techniques. They can understand and can analyze the complex and nonlinear relationships between the conditioning and triggering factors for multiple hazards. The GLM, which is a generalized linear model, people has already used. The forest-based classification and regression model have been used. Specifically, support vector machine is much used in these kind of studies. So the important thing while switching from the subjective and objective methods toward the machine learning in multiple hazards, these models actually can contribute more perfectly than these models. I mean, in subjective methods, what we do objective methods, sorry, we actually give importance to factors, and then some expert opinions are actually included in those models. But machine learning actually does not rely on the expert opinions. Even that also an option in the machine learning, but it can bring enormous advancement in multi-hazard susceptibility mapping. It can directly classify the natural hazards. It can directly interpret the data. However, we are giving it a training data. We will discuss it later. So people are focusing on the machine learnings in multiple hazards. However, the Northern Pakistan is, as we all know, is exposed to multiple hazards, including landslides, debris flows, floods, gulfs, and earthquakes. The reason behind is that it have a unique topography, have steep slopes and deeply incised valleys, which can increase their risk to landslides and debris flows and other hazards. And also, the effects of climate change in northern Pakistan are increasing due to rising temperature. Like in one study, they have highlighted at an average of 0.85 degrees Celsius since 1980. And also, the shifting monsoon patterns, and these all factors actually increase the frequency of extreme events, and specifically the active tectonic zones. The North Pakistan, specifically, if we talk about the Hunza district, so the active tectonic activities can cause secondary hazards as well. I mean, seismic have already caused many landslides and debris flows in district Hunza. Even these all are well recorded and research studies and in many other reports, local news, etc. So the geological factors, including active tectonics and active fault, lead to small and to large magnitude of earthquakes. These earthquakes have caused, as I mentioned, many secondary hazards. A climate change further accelerates glacial melting and alters precipitation, increasing the risk of gulfs, which severely impact downstream communities. So all these things can bring the focus to study the multiple hazards in northern Pakistan. Now, the study area for this study was the district Hunza, In North Pakistan, with its unique topography, tectonic settings, geological features, and climatic factors that facilitate multi-hazard occurrence, as I have already mentioned in the introduction section, the overview section, tectonics, loose materials, topography, and all these contribute to the occurrence of multiple hazards. Geographically, the district Hunza consists of three regions: Upper Hunza, Gujal, Central Hunza, and Lower Hunza. So it has a total area of 11,440 square kilometer and hosting some largest valley glaciers including Bathura 59 km square, Pasu 24, Golkin, Hesper, and Althar. It also has a high elevation area. It ranges from 1814 to 7,749 meter above sea level. So the river Hunza draining the area is fed by the melting of surrounding glaciers and is one of the major tributaries of the Indus River downstream. Thus, one of the crucial water resources for the entire community. So in district Hunza, usually the peoples are relying on the river Hunza water for their agriculture activities, and many activities are relied on this river. The unique geological settings marked by thrust faults, fracture rocks, and exposed geomorphology combined with human interference such as deforestation and infrastructure development. As we all know, the CPEC project is currently continue in northern Pakistan. That's a huge development in northern Pakistan. But still, that is actually under the umbrella of number of hazards. I mean, multiple hazards can cause a destruction to the CPEC project and many other projects, and also it can add cost and delay the construction and sustainable chain through the only, which is the CPEC only route between the China and Pakistan. So the Athabad landslide, Mayun landslide, and recent event of Shisper Glacier in 2020 and 2022 has also caused the flood in the Hassanabad Nala. So all these hazards are actually well recorded, and people have studied it in many regions. In many research paper they have shown all these things. So, what make us focus on this study? Why we are actually focusing to study multiple hazards in District Hunza specifically? The District Hunza has witnessed and been exposed to multi hazards, while many studies have focused on individual hazards. That didn't consider the hazards as multiple. An integrated approach was actually missing. However, relying on single hazard assessments for disaster risk reduction policies and measures could lead to an underestimation of the prevailing risk, specifically caused by the multiple hazards. So the studies of Ahmad et al., Bacha et al., Hawass et al. 2020. So all these studies has actually worked on the single hazard, which is, I mean, a next step for us to study the multiple hazards, where we have seen many hazards like secondary hazard can be caused by the primary hazard, like seismic has caused many secondary hazard, landslides, debris flows. So we will use the machine learning in this study. And the machine learning, this is the first attempt in northern Pakistan to utilize the machine learning in northern Pakistan, and this will serve like the first baseline for other studies as well, like using the machine learning in the high mountainous areas. So materials in this study have we have used a loss pulsar sensor and to compute the topographic features like the elevation, slope, aspect, plane curvature, profile curvature, TWI, streams, and all these factors, like the streams, all these were computed from from the Elos Pulsar Dam, which has 12.5 meter spatial resolution. So mean monthly rainfall data was acquired from the Global Precipitation Measurement website, sensor, a GPM, and Sentinel-2 Copernicus satellite images were used for land cover map and normalized difference vegetation index. The the Sentinel-2 images were used for the land cover mapping and for the NDVI, normalized difference vegetation index mapping. Lithology map was digitized from the geological map of northern Pakistan, which was developed by the Sirli et al. 1996. The hazard maps. So in this study, I worked on the flash flood susceptibility. We have developed landslide studies. We have students, they have worked on different hazards. All these papers have already submitted to different journals for the publication. So soon many in these papers have already accepted, and currently still few are under review. So we have integrated all these hazards into one specific hazards, that is called integrated multi-hazard map. The landslide and debris flow susceptibility map was sourced from Yasin et al., and all these hazard maps was acquired from different authors. While the flash flood susceptibility map were missing for this area, that's why we have developed in this study by using the machine learning model. So machine learning we have used in this work play a key role, like we have integrated the all the hazards into one integrated approach. And second work which we have done in this paper or with mapping the flash flood susceptibility for the district Hunza using the same machine learning forest based classification and regression model. The hazard locations were determined by the uh, in this study we have actually classified each hazard map into different sections, like zones like very low hazard, moderate, high hazard, and very high hazard zones. And were given values like 1, 2, 3, 4, 5, with 5 representing very high hazard, and 4 representing high, 3 representing moderate, 2 representing low, and 1 representing very low hazard. So to make it standard and normalized, we have resampled all the hazards into 12.5 meter of pixel resolution and standardized into one from 1 to 5 values. So we have actually, the second step was to collect the samples of both hazard and non-hazard locations. The hazard locations were determined by identifying areas on each hazard map that showed the highest susceptibility level, such as high and very high classes, while non-hazard locations were randomly sampled from moderate and low susceptibility classes. Random sampling also ensures the dataset's spatial distribution through the entire study. So what basic concept behind this technique is that we have the hazards. What we did with this model, we have targeted the very high hazard zone of hazard map and given it a value of 1, and the very low hazard zone was given a value of 1, and same for very low, moderate. These were given a value of 1, which means a very low hazard zone. The reason behind is that the susceptibility modeling, whenever we are working with the machine learning, the susceptibility modeling usually rely on the samples from both hazards and non-hazards. So the equal number of hazard and non-hazard locations are required whenever you are working with the machine learning, specifically the forest-based classification. You have to find this inventory data, and then train the model. So we have digitized the point data in a point format from each hazard map, a hazard zone, given it a value one which is representing a very high hazard zone, 0 as non-hazard zone. So this process can actually simplify the data. I mean, everyone can understand that the hazard map now, that the map is actually showing the hazard and non-hazard with value 1 and value 0. Random samplings we have done for the non-hazard location. Specific numbers of hazard locations we have digitized from each hazard map, and the non-hazard location was randomly sampled to all the process. And this process basically provided the input data for further machine learning process. A total of 120 points were defined for landslide accessibility, 120 as a non-landslide points, 90 for seismic, 90 for non-seismic, 10 for bluff, 10 for non-bluff regions. Similarly, we have done for this engine. The flash flood, we have digitized these numbers from few papers like the paper from Bag et al. Or I mean, we have reliable literature for this, as we don't have a real-time data for this. That's why we have utilized our data from literature, as well as we have gathered the data from the field. So this binary classification model, as I mentioned, it works with 0 and 1. We have identified the location from non-flood and flood for all the hazards. I mean, flood, let's say a hazard location and non-hazard location. So at the end, we have divided all these data into two chunks. One is the training, and the other is the test. 70% was used for the training purpose, and the 30% was used for the validation or importance measurement and for variable determining and tuning process. During the whole process we have done. So in language susceptibility, we have considered 12 factors, which we will discuss after this slide, related to 12 factors, how they contribute to the final map, and what factors we have actually considered for study. So let's move to that. So these are the methods showing effect, elimination, stop degree, all the file literature, land use, and ABI, lithology, TWI, distance to stream, distance to river, road, distance to road. Land play a key role whenever someone is making the flash flood, has to rely on some factors influence factor level, one of them a key factor playing a key role in the flash flood determining if the area has high vegetation, high vegetation or low susceptibility of flooding, predicted there. Negative correlation is occurs between flooding and vegetation density. Vegetated areas help absorb water and slow down the risk of surface runoff and flooding. On the other hand, irrigation surface such as roads, residential area, and bare lands contribute to increased water runoff as highlighted in our maps. These factors in turn elevate the likelihood of flooding in such areas. So in this study, we have mapped few landfall types, land use type, water, forest, snow cover, marine, agriculture, and delta areas. Specifically, the normalized difference vegetation index also play a key role in this study. The NDVI play a key role in flood mapping by indicating vegetation density, which affect the surface runoff. So if we have more agriculture and vegetation in an area, so we have less chances of flash flooding. I mean that actually uh, just absorb the water and they can lay down. I mean, their absorption can slow down its flow. The flash flood slow can flash floods can be slowed down within a vegetation area, and also the runoff will be lower in agricultural areas. Topographic wetness index is an essential tool for understanding the spatial distribution of wet and dry areas, providing critical information on water flow direction and accumulation. Areas with high TWI values are particularly prone to flooding because they represent locations where water collects more easily, either due to low-lying terrains or areas with slower drainage. Rainfall is the key factor for the flash flood susceptibility mapping. Its intensity directly impacts flood risk. With heavy rainfall, we have more chances of river to overflow and cause flooding. The rainfall, if we have more rainfall in an area, that means we have more chances of flash flooding in that area. The slope is another crucial factor for influencing factor for flash flood susceptibility mapping. Steeper slopes cause faster surface runoff, reducing water absorption and increasing flood risk in downstream and can cause impacts and destructions to the downstream communities. So flatter areas tend to accumulate more water, making them more prone. As an image is, if you can see, like simply the elevation areas, they can have more faster runoff of water. The water can flow down quickly, so the valleys or the low-lying areas can be affected uh, more as compared to high elevation areas. Curvature is another important factor. The terrain shapes, indicating how terrain shapes water flow. Flat areas have the highest flood risk as they retain water very high risk, while convex areas encourage drainage, moderate risk. Concave areas with inward slopes reduce flood risk significantly. Aspect is another factor. It impacts flash flood risk by influencing slope moisture and runoff. The south facing slopes are drier, leading to higher runoff, while north facing slopes retain more moisture and may flood when saturated. In mountainous areas, aspect also affects snow accumulation and melt, contributing to flash floods. Proximity to stream significantly, the distance to stream is another crucial factor. If we are much closer to the stream, so we have more chances to be flooded, I mean to be impacted from flood, especially in mountainous regions. Locations near streams face rapid intense flooding due to fast water flow, steep slopes. So distance to road is another factor, and similarly as lithology. So the forest-based classification, the machine learning algorithm which I have used in this study, which is one of the most crucial model, I would say. When I was working on this model, it was performing really well. There is few other models like support vector machine, GLM, and other models, XG at a boost. So all these can contribute to the natural hazards mapping. But this supervised machine learning method combine the decision trees. With each decision tree, it is casting a unit vote for the most popular class. This method is actually an adoption of the Bremen's algorithm, a random forest algorithm. So what it do, it actually cast the votes for the most popular class. By most popular class, we means the most important hazard or the factor that is used in this study. So DTs are usually built using the bootstrap samples, allowing duplicate observation. It makes duplicates of data. It omits some original observation, and then they predict the final output based on these decision trees. So FBCR model is also a natural nonlinear modeling tool that estimates variable importance importance and hierarchy in classification. It is widely used in natural hazards forecasting, like Lee et al. 2007 has used. And another thing, the binary classification model require inventory of hazard locations. So as I already have discussed about the inventory of hazards, how we have developed this inventory, giving it a value 1 and 0. In the right side, you can see the inventory map. So the model out of bag error is one of the key power in this model. This can provide an internal measure of model accuracy without the need for a separate validation. This model can provide its own validation capabilities. I mean, it can measure the accuracy and the error probabilities or error capacity it can provide without us. I mean, we don't need to do the separate validation set when creating and using this forest based classification. Typically, with around two-thirds of the data selected through both bootstrapping and which can be used for the out-of-bag error estimation. So, and then the lower OOB error indicates better model accuracy, and if we have high OOB error, so that means we have higher error in the final integrated model. The flash flood susceptibility model output, these are the importance of the parameters which we have used in this study. All these geo-environmental variable for flash flood susceptibility mapping was estimated, and the most important variable for predicting flash flood susceptibility or rainfall. The machine learning, the FBCR model, it actually use its own index importance degree analysis. It used the mean decrease Gini impurity, which is a metric in the forest-based classification for assessing the importance of each hazard or the parameters importance, how they have contributed to the integrated multi-hazard map or the final output. So the main decrease Gini importance actually split the data into pure groups. A pure group means that the samples are mostly from the same category, like high or low. The data is divided. Okay, in this model, the data is divided into high or low categories. So the mean decrease Gini actually shows how much each feature on average improves these splits across all trees, and then they predict and cast the vote to each important factors. The aerial coverage of very high to high flash flood susceptible areas was 536.306 and 131.431.16% kilometer square. while the moderate, low, and very low were followed by the 18, 48, and 27.93%. So this is the integrated multiple hazard map. As I have already discussed about the MDG, mean decrease Gini importance. So we have actually calculated the hazards importance, and then later we have verified all those importance by interacting with the people, like which hazard they usually faced or experienced in district Hunza. So we have conducted an extensive field survey. We have relied on the available literature, local experts, opinions, and we have engaged with decision makers. The importance of each hazard was then considered. After all these literatures, field surveys, and expert opinions, then we have considered the importance of each hazard into integrated multi-hazard map. So in the multi-hazard maps, if we see like the lower Hunza is usually under the high multiple hazard zones. The reason behind can be that many human activities are right now happening there. The pixel values for, we have given it different names. We haven't done like the very low hazard zone, integrated hazard zone, low integrated hazard zone, moderate. No, this is the first approach in district Hunza. For in the northern Pakistan we have used, like we need to see where the hazards are overlapping. Actually that thing is important and missing through all these studies. Everyone need to focus. Even in these advanced studies, this cascading events can be observed from these hazards. One region uh, can be prone to multiple hazards. If you see, if everyone can see that the FF, LS, GF, these numbers, these short names, these representing the debris flow for DF, LS landslide, GLOF. So these sections are actually prone to multiple hazards, not only one hazard, but can have an impact of multiple hazards. As you can see in insets and inset maps, so all these things are mentioned there. The pixels of the final integrated multiple hazards were reclassified within GIS and into 8 classes: a low hazard, LS, FF, as I have already mentioned, and these are the areas which we have calculated from the final integrated multiple hazard maps. So out of big error, I have already mentioned about this. This is a key matrix for the error estimation in within machine learning. It can also provide an unbiased estimation of the model performance, and itself the forest-based classification actually run the model for 100 times. I mean, to assess and move closer to the characteristics that each parameter is reflecting, each factor is contributing to the flash to the final integrated map. These percentages, if you see in the image reflecting, the percentages show how well the model captures the variability in each hazard, with higher values of 33.44 to 32.84 indicating a better fit of the model data. So all these are the variations. If less lower the number we have, lower the percentage, that means we have good validation of the model and good number of results. So this is the conclusion. The integrated multi-hazard map exposes the reality that a substantial portion of the district faces the threat of multiple hazards. Central and lower portion of the study area and areas along the road have also shown a significant proneness to multiple hazards, like the CPEC route specifically. In this study, we have also mentioned that it is prone to multiple hazards. So these things calls for quick attention to risk reduction and mitigation. Considering more than one hazard can be an effective way forward approach for multi-hazard management of mountainous environment facing multi-hazard challenges. It could help in quantifying vulnerability and risk. Planners can estimate multi-hazards, informing land use decisions for a more resilient future. It identifies unsafe areas for development, and it also can raise his awareness supporting sustainable resources management. So the final map, as we have shown a significant variation. If we talk about this final result, as I have already mentioned in the conclusion, significant area is prone to multiple hazards, and many areas are actually showing the overlapping of multiple hazards, such as debris flow, landslide, flash floods. If you see, if everyone's seen the map, the northwestern region close to Barakhon village and Khunjarab Pass in F section, I mean the NSIT map F, that is showing the increased erosion. Many hazards are overlapping there. Many human activities are not happening there, but still many factors are contributing in northern Pakistan. Like the A, if you see an NSIT map of A, human activities are usually impacting it and causing multiple hazards in these regions. So, what way forward, what people should do with these maps? If someone have these maps, so what they can do with these maps, they can evaluate the exposure of elements that are at risk. Exposure of elements is an important factor that can show us which parameter, like the house, the roads, the section of the roads, bridges, all these are exposed to hazards or not. The exposure can be assessed through this hazard map. Vulnerability is another important factor. This map can be utilized for vulnerability analysis. There is different kind of vulnerability, like the physical vulnerability can be conducted based on this map. Everyone can consider the household, the infrastructures, the roads, the section of the roads, the peoples that are exposed to multiple hazards. So this map can help us in many aspects, like the economic risk, even land values, the economic exposure and economic vulnerability, social vulnerability, human exposure. All these can be done with that map. And at the end, we can calculate the total risk from the combination of integrated multi-hazard map. By the total risk, I mean, if we talk about the risk is actually the combination of uh, vulnerability, exposure, and hazard. So all these can combinedly make a one risk map that can contribute on a large number to societies. These demarcations are the need of the societies right now. In these current highly exposed northern Pakistan, these studies are more required. Future exposure of elements at risk. These can be done on the hazard map. The future is key. Everyone, if someone start working on the exposure analysis, elements at risk for the future study is key. Actually, we need to know how the future will look like in these mountainous areas, which areas will be much prone to these hazards. So we need to project the future and then assess the elements which can be in future, which can be at risk. So all these analysis, we are also working on this, and I'm also highlighting we can also contribute to people so that we can provide this data to start working on the multi-hazards the exposure of the element vulnerability and total risk. Thank you.
Yeah, sure. Thank you so much for the wonderful presentation, first of all, Ismail.
Thank you so much.
But yeah, I'm a little afraid of some things I would like to confirm for you. For example, you talk about multi-hazard, right? So in the presentation, we saw about flood mapping, susceptibility mapping. Uh,
Yes, yes.
we did not cover other hazards, like for example landslides or earthquakes, and then we combine it, for example, like because it is the integration of different multi hazards. We discussed only about flood susceptibility, but at the end of the presentations, like we saw a susceptibility map of different hazards, rather than we did not study in the beginning or in the middle about any other hazards, but at the end we got the map of like the susceptibility of landslides, earthquakes, debris flow, and so many other things. So I'm afraid of that. This is first. And second thing about the methodology, about the uh, forest-based classification and regression method. I'm afraid about using this single model to map these multi-hazards. So, like, for example, how we can say about this model that it will be better than using other machine learning or deep learning techniques, rather than comparing it or using it parallel with this model.
Thank you so much, sir. Thank you so much. Sir, in the presentation, I have mentioned actually, I am working as a research assistant at the National Center of Excellence in
Yeah.
Geology. And we are working under the project CPAC project. We have
Mhm.
students that have worked and they have already